Imagine a universe so vast, so mysterious that the very ground we stand on, our cosmic home, the Milky Way, might be floating in a desolate void, a region so empty it could unravel the laws of physics as we know them. This isn't science fiction. It's the heart of a cosmic enigma that's shaking the foundations of everything we believe about the cosmos. The universe is expanding, stretching out like a balloon, inflating at unimaginable speeds. But something's wrong. Two ways of measuring this expansion are screaming different answers, and the discrepancy is so profound, it's dubbed the Hubble Tension, a clash that's tearing at the seams of our understanding. What if the Milky Way is sitting in a giant cosmic void, a bubble of emptiness so massive it's skewing our view of the universe? This void, known as the KBC void, could be the key to unlocking this mystery, or it might just break physics as we know it. Buckle up, because we're diving into a mind-bending journey through the cosmos, exploring the Hubble tension, the eerie emptiness around our galaxy, and why this could rewrite the story of the universe itself. Get ready for a roller coaster of shocking discoveries, emotional revelations, and a cosmic puzzle that might just change everything. Let's start with the Hubble tension, a cosmic conundrum that's got scientists scratching their heads and questioning the very fabric of reality. The universe is expanding. Galaxies are racing away from each other, carried by the relentless stretch of space itself. To measure how fast this is happening, we use something called the Hubble Constant, a number that acts like a cosmic speedometer, telling us how quickly the universe is growing. It's not just a number. It's the key to understanding the age, size, and ultimate fate of the cosmos. But here's where things get wild. Two incredibly precise methods for measuring this constant are giving us two wildly different answers. One method looks at the early universe, peering back to the faint glow of the Big Bang itself, a snapshot of the cosmos when it was just a baby, 380,000 years old. This glow, called the cosmic microwave background, is like a cosmic fossil, carrying clues about how the universe began. Using this, scientists calculate a Hubble constant of about 67.4 kilometers per second per megaparsec, a megaparsec being roughly 3.26 million light-years. This number comes from our best model of the universe, a framework called lambda cold dark matter, which assumes the cosmos is made up of ordinary matter, mysterious dark matter, and an even stranger force called dark energy, pushing everything apart. It's a model that's been tested, refined, and trusted for decades. But then there's the other method, the one looking at the universe closer to home. Scientists use objects like Cepheid variable stars, stars that pulse with a predictable rhythm, making them perfect cosmic rulers, and Type Ia supernovae, exploding stars with a consistent brightness that lets us measure distances across the cosmos. These are called standard candles, and they're the gold standard for gauging how far away things are in the nearby universe. When scientists use these to measure the Hubble constant, they get a higher number, around 73 kilometers per second per megaparsec. That difference might sound small, but in the world of cosmology, it's a screaming alarm bell. These measurements aren't just off. They're off by so much that random errors can't explain it. This isn't a glitch. It's a full-blown crisis. The early universe says one thing, the local universe says another, and the gap between them is growing wider with every new observation. It's like measuring the speed of a car with two different speedometers and getting answers so different you start to wonder if the car itself is broken. What makes this even more jaw-dropping is the latest evidence. The James Webb Space Telescope, with its razor-sharp vision, has zoomed in on those Cepheid stars and confirmed the higher Hubble constant from local measurements. This isn't some fuzzy data point. It's crystal clear evidence that the discrepancy is real. The telescope's observations have ruled out old excuses like calibration errors or blurry measurements. The tension is no longer a maybe. It's a blazing signal that something fundamental is wrong. If the early universe measurements are right, our models of the cosmos hold up, but the local measurements suggest something else entirely. Could dark energy, that mysterious force driving the universe's expansion, be changing over time? Are there unknown particles or forces we've missed? Or is the very structure of the universe not what we thought? The stakes are massive. If we can't agree on how fast the universe is expanding, we can't pin down its age. Estimates could shift by hundreds of millions of years. Worse, it means our understanding of the cosmos, built on decades of careful work, might be missing a critical piece of the puzzle. This isn't just a number, it's a crack in the foundation of physics itself. Now let's zoom in closer to home, because the answer to this cosmic riddle might not lie in the distant stars, but right here, in our own backyard. Picture this. The Milky Way, our galaxy, isn't floating in a typical slice of the universe. Instead, it's sitting in a colossal void, a region of space so empty it's like a ghost town in the cosmos. This is the KBC void, named after the astronomers who first proposed it, a mind-boggling stretch of space roughly 2 billion light-years across, with about 20% less matter than the average universe. Imagine a city where most of the buildings, people, and cars are gone, leaving just a handful of structures in a vast, empty landscape. That's the KBC void, a cosmic desert where galaxies, stars, and gas are scarce, and the Milky Way just happens to be one of the few residents. This void isn't just a curiosity. It might hold the key to the Hubble tension. If we're living in this underdense region, it could be messing with our measurements, making the universe's expansion look faster than it really is. Here's how it works. In a void, there's less gravity holding things together. Galaxies in denser parts of the universe are pulled inward by the weight of surrounding matter. But in a void, there's less of that pull. This means galaxies in the KBC void might be drifting outward faster than they would in a normal part of the cosmos, creating the illusion of a faster expansion rate when we measure nearby objects like Cepheid stars or supernovae. It's like being on a raft in a calm river versus one in a rushing current. You'd move faster in the current, even if the river itself isn't changing. This effect is tied to something called the integrated Sachs-Wolf effect, a quirk of general relativity where light, traveling through a void, loses a tiny bit of energy, shifting its wavelength and making distances appear slightly different. If the KBC void is real, it could explain why our local measurements of the Hubble constant are higher than those from the early universe. It's a natural, elegant solution. No need for exotic new physics, just a weird quirk of where we happen to live. But here's the kicker. This idea challenges one of the biggest assumptions in cosmology, the cosmological principle. This principle says the universe on large scales is homogeneous and isotropic, meaning it looks the same everywhere, no matter where you stand or which direction you look. It's the bedrock of modern cosmology, the idea that we're not in a special place, just one random spot in a uniform cosmos. If the KBC void is as big and empty as some think, it throws that principle into question. A void 2 billion light-years wide isn't just a small wrinkle. It's a massive dent in the universe's uniformity. If we're living in a cosmic bubble, our view of the universe might be skewed, like looking through a funhouse mirror. This would mean the universe isn't as even as we thought, and our models, built on the assumption of uniformity, could be fundamentally flawed. It's a gut punch to everything we've built our understanding on, and it's both thrilling and terrifying. The evidence for the KBC void is tantalizing, but not ironclad. Galaxy surveys, which map the distribution of galaxies across the sky, show hints of a lower-than-average density in a huge region around the Milky Way. Redshift studies, which measure how light from distant galaxies stretches as they move away, also suggest we might be in an underdense zone. But these are like clues in a cosmic detective story. Strong, but not definitive. Critics argue the void might not be as deep or wide as claimed, or that it's not enough to explain the full Hubble tension. Others point out that a void this big should leave a mark on the cosmic microwave background, a kind of shadow or ripple in the early universe's glow, but those signals are faint or missing entirely. To settle this, astronomers are doubling down. They're studying supernovae outside the supposed void to see if their measurements differ. They're mapping galaxy clusters and their motions to check for signs of an underdense region. They're diving into deep surveys of the universe's large-scale structure, trying to piece together whether the KBC void is real or just a mirage. Every observation is a piece of the puzzle, and the picture it's forming is both exhilarating and unsettling. But the KBC void isn't the only player in this cosmic drama. The universe is full of voids, superclusters, and filaments, a web of structures that make up its large-scale architecture. Some researchers are looking beyond the KBC void to other nearby structures, wondering if a complex patchwork of dense and empty regions could be skewing our measurements. If the universe is lumpier than we thought, with vast voids and massive clusters tugging galaxies in unexpected ways, it could explain the Hubble tension without needing a single giant void. This idea is gaining traction, fueled by observations of bulk flows, huge, coherent motions of galaxies across billions of light years. These flows suggest the universe might be more dynamic, more uneven than our models predict. If true, it's not just the KBC void that's shaking things up. It's the whole cosmic neighborhood, a chaotic dance of matter and emptiness that's throwing our cosmic speedometer out of whack. Let's take a step back and feel the weight of this. The Hubble tension and the KBC void aren't just abstract science problems, they're a profound challenge to how we see ourselves in the universe. For centuries, we've grappled with our place in the cosmos, moving from the center of everything in ancient models to just another planet orbiting an average star in a typical galaxy. Now we're facing the possibility that our galaxy isn't even in a typical part of the universe. We might be outliers, living in a cosmic backwater that's distorting our view of reality. It's humbling, but it's also electrifying. The idea that our home could be so unique, so peculiar, sparks a sense of wonder and urgency. What does it mean to be in a void? Are we alone in this emptiness, or is the universe full of such quirks, waiting to be discovered? The emotional pull of this mystery is undeniable. It's a call to explore, to question, to push the boundaries of what we believe is possible. As we dig deeper, the implications grow even wilder. If the KBC void is real and affecting our measurements, it could mean we've been misreading the universe's story all along. The Hubble constant isn't just about speed, it's tied to the universe's age, its size, and its ultimate fate. A faster expansion rate could mean a younger universe, one that's hundreds of millions of years less ancient than we thought. It could shift our understanding of how galaxies formed, how dark energy behaves, or whether new forces or particles are lurking in the shadows. Some scientists are exploring radical ideas like tweaking general relativity itself. Theories like modified Newtonian dynamics or emergent gravity suggest gravity might work differently on cosmic scales, naturally explaining anomalies like the Hubble tension or giant voids. Others are looking at exotic particles, like sterile neutrinos, which could smooth out the universe's structure and make voids like the KBC more likely. These aren't just tweaks to the model, they're revolutionary ideas that could rewrite the laws of physics. The search for answers is pushing technology and imagination to their limits. New telescopes, like the Nancy Grace Roman, Space Telescope and Euclid, are gearing up to map the universe with unprecedented detail, hunting for clues about voids, expansion rates, and the cosmic web. Gravitational wave observatories are joining the fray, using ripples in space-time, from colliding black holes or neutron stars, to measure the Hubble constant in a completely new way. These standard sirens don't rely on light, so they're immune to the tricks of voids or gravitational effects. If they confirm one side of the Hubble tension, it could tip the scales. Meanwhile, artificial intelligence is stepping in, running massive simulations of the universe to test every possible scenario, from standard models to wild alternative physics. These simulations are like cosmic laboratories, letting us experiment with ideas too big to test in real life. Every new observation, every new simulation, brings us closer to cracking the code, or realizing the code was wrong all along. But let's not lose sight of the human side of this. The Hubble tension and the KBC void aren't just about numbers or equations. They're about our quest to understand our place in the cosmos. Every scientist working on this puzzle is driven by the same curiosity, the same awe that's fueled discovery for centuries. They're staring into the abyss of the unknown, asking questions that could change how we see the universe and ourselves. It's a journey filled with frustration, hope, and moments of breathtaking clarity. When a new observation comes in, when a simulation matches reality, it's like a spark in the dark, a glimpse of truth that makes the struggle worth it. And for us, watching this unfold, it's a reminder of how vast, how mysterious, how beautiful the universe is. We're not just passive observers. We're part of this cosmic story, living in a galaxy that might be at the heart of one of the greatest mysteries ever uncovered. As we look to the future, the path forward is both daunting and exhilarating. The tools we're building, the questions we're asking, and the ideas we're daring to explore are pushing the boundaries of what's possible. The Hubble tension could be a fluke, a hidden error waiting to be found. But it feels bigger than that. It feels like the universe is whispering something new, something we're only beginning to hear. If the KBC void is real, it's not just a hole in space, it's a hole in our understanding, a challenge to rethink everything we know. And if it's not, if the tension points to new physics or a lumpy, uneven universe, that's just as thrilling. We're on the edge of a revolution, one that could redefine the cosmos and our place in it. The universe is calling, and it's up to us to listen, to explore, to dare to imagine what lies beyond the void. Stay curious, keep looking up, and let's uncover the secrets the cosmos is hiding. The answers are out there, waiting in the emptiness, ready to change everything. Thank you for joining us on this journey through the wonders of space. Your support makes it possible to continue sharing the marvels of the universe with the world. We can keep exploring the stars and uncovering the secrets of the cosmos. Until next time, keep looking up